Welcome to part 2 of Identities, and this is where we're going to learn how to really verify a full-blown, little bit more difficult identity instead of just simplifying expressions. So this is what it means from a direction standpoint to verify an identity algebraically. It is proof-like. In other words, the point of verifying an identity is to show work. And I know that sometimes when you're doing numerical calculations, teachers don't always require every single step, but this is one of those lessons where you want to overshow your work, not under. So, what does it mean? It means you have to algebraically show steps to make one side of the equation match the other. It is proof-like without having to give a reason. So when you did two-column proofs in geometry, you usually made a statement, and then on the other side you gave a reason. Your audience would be your peers or people that have had more math beyond honors pre-calc. So that's why you don't really have to have a reason, but as you write down your statements, somebody who is reading them is going to have to logically conclude how you got from one step to the other. So with that said, that's why it is important for you to overshow your work than under. Don't leave anything under assumption. This is a quote from your textbook, which I like. Let me erase all this other stuff. And this is the analogy that I give students about verifying an identity. You know, a lot of you like math that is recipe-like. You like math that is step 1, step 2, step 3. But that's not really what an identity is like. There is no well-defined set of rules to follow in verifying trigonometric identities, and the process is best learned by practice. You have to be willing to try something. If you're going to just stare at it and do nothing, you can think about it for a while, but you have to try something. What are those somethings? Well, here we go. Guidelines for varying trigonometric identities, and they are located in your text. I'm not sure that that page number is quite accurate. I think that's from an old text. But if you refer to section 5.2 of your textbook, you will see these guidelines there. First, you want to work with one side of the equation at a time. And believe it or not, it's more often to work better with the more complicated side first. Why? Because there's more to do. And I love number 2. And this is why you practiced in part 1. Look for opportunities to factor an expression. You did a lot of factoring in the previous assignments. Sometimes you have to get a common denominator and add fractions. I'm going to show you some problems where squaring a binomial helps or creating a monomial denominator helps. But you're going to have to use some of your algebra skills combined with looking for opportunities to find the fundamental identities. And that's why this is not a recipe. Sometimes you have to use an identity first and you don't know which one it is. You have to try something. So I always keep your goal in mind. I can't stress that enough. Look at what trig functions are in the final expression you want. If everything in the final expression is tans and you are lost in cosecants, you're probably not on the right track. And we practiced some of this in the previous part. Sines and cosines pair up well. So when in doubt, put everything in terms of sines and cosines. Secants and tangents are well, and cosecants and cotangents do the Pythagorean identities. Always try something. Because I think what a lot of times kids feel like is, I get this, I know what I'm doing, but if you don't practice, you don't learn how to get inside the vortex, because even making an attempt that leads to a dead end, I think provides valuable insight. I think you learn more from your mistakes. All right, here we go. Example 7. This is an example of a full-blown identity because what you were doing in the previous section is you were just evaluating expressions and simplifying them, but now you have an identity where you have an equal sign. You have not yet shown or verified that this is a true statement. So you may not use equation operations. This means you can't add something to both sides. You cannot subtract something from both sides. You cannot multiply. You cannot divide. You cannot square both sides. You cannot manipulate over this equals. Everything you do, you have to manipulate on one side or the other to make them match. So as we go through, I'll try to show some examples of that, but that is, I guess, the biggest vortex or one of the biggest mistakes kids fall into. All right, here we go. For the sake of the video, I'm probably not going to ask as many questions like I would in class, but this is how I would try to set it up expeditiously. It's very clear that the left-hand side is more complicated than right-hand side. I don't know what I could do to this cotangent to turn it into these two binomials that I'm multiplying by each other. So I'm going to start with the more complicated side, which is the left. Right now, it is completely valid that you could turn secant into 1 over cosine. You could turn tangent into sine over cosine. And friends, that is legitimate. And we're going to actually do some of that next, but I try to not deal with fractions until I absolutely have to. I'm going to do some algebra. I'm just going to FOIL this out. So when I FOIL this out, I'm going to get the secant of theta, the cosecant of theta, plus the secant of theta, minus the tangent of theta, cosecant theta, minus the tangent of theta. Notice how all I did was some algebra to one side. So at this point, friends, you can't add a tan to both sides. You cannot, all I can do is simplify this expression, and our goal is to make it look like the cotangent of theta. So this is a hot mess. I have all kinds of trig functions, so now I am going to go and put everything in terms of sines and cosines. So this is going to be 1 over cosine theta by the reciprocal identities times 1 over the sine theta by reciprocal identity, plus 1 over the cosine theta by reciprocal identity, minus sine theta over cosine theta by quotient, times 1 over sine theta, and I like what's happening there, minus sine theta over cosine theta. Again, this might not be the only way you see how to verify this, but this is the most popular way that I see students. Okay, so what we just did there is we applied several fundamental identities. Now I'm going to do some algebra. This is one term because it's multiplication. This is one term. Those are being multiplied. It's one term. This is one term. In this term, the signs cancel, leaving me with 1 over cosine theta. 1 plus cosine theta minus 1 over cosine theta, they undo each other. So I am left with 1 over the cosine of theta sine of theta minus sine theta over cosine theta. And you're like, okay, what am I going to do now? Well, we have an opportunity right here where you have two rational statements. My goal right now is to get this into one rational statement. So I'm going to multiply by sine theta over sine theta because that's 1. And I get 1 minus sine squared theta all over the common denominator cosine theta sine theta. Again, notice how I don't have to put a reason, but hopefully you're hearing me verbally say that. And that is what you need to be doing as you go through these identities. You need to be doing that self-talk, because if you can't justify how you're verifying the identity, then you probably can't do it. All right, so what are we going to do next? Well, in my next step, what should be ringing in your head is I've got a power of 2. That means I need to look at my Pythagorean identities. 1 minus sine squared is cosine squared. And hopefully you see it. One of the cosines on top cancels the cosine on bottom. Cosine theta over sine theta gives me cotangent of theta. Those equal each other. And now you have successfully verified this identity. Let's look at example 8. Okay, on example 8, yep, you're looking at this, you're like, this is a hot mess. So again, I'm going to start with the left side and make it look like the right, because it's more complicated. None of these have a squared term. So the Pythagoreans don't work, but maybe I'll be able to kind of do something that helps. And maybe, because we do have that Pythagorean identity that relates tangents and secants. So because, again, I have two fractions, I'm going to go ahead and get this to be a common denominator. So I'm going to multiply the first rational expression by tangent theta over tangent theta, which gives me tangent theta squared. I'm going to multiply this by 1 plus the secant theta. So this gives me 1 plus secant theta, the quantity squared, all over the tangent of theta, 1 plus the secant of theta. And I'm going to give you a tip right now. My opinion is that I would not distribute. Why? Because my goal is to eventually get to 1 over sine theta. And so it's really not necessary. My point of expanding, and when you learned about rational expressions in Algebra 2 trig, is you need to expand the numerator, and our goal is to be able to cancel out factors of 1. So, I mean, it's not wrong to distribute, but my opinion is I would not distribute until it was absolutely necessary. All right, so here's what I'm noticing in the numerator. In the numerator, I have a squared tangent, but this isn't squared. So for me to use Pythagorean identities, I need everything squared. So I'm going to go ahead and expand 1 plus secant theta and consider it as 1 plus secant theta times 1 plus secant theta, and expand that using algebra. So this is what we mean by you have to try something. You have to use your algebra skills and your identities, and I'm not giving you the order. You just have to kind of figure it out like a puzzle. So I'm going to get 1 plus 2 secant theta plus secant squared theta all over tangent theta 1 plus secant theta. Again, you can get yourself in the vortex. I'm just going to kind of cut to the chase due to the video. What I'm noticing is I've got a secant, I've got a secant, I've got a constant, and I have a tangent. So maybe there is a way for me to turn tangent into a secant so that I have all the same trig function in the numerator. So let's replace that with the Pythagorean identity, secant squared theta minus 1, and then I'm going to rewrite the rest of the numerator. And then rewrite the denominator. And what do we notice is going on algebraically upstairs? The 1's cancel. And then I am left with 2 secant squared thetas when I combine like terms, plus a 2 secant theta. And friends, I'm really liking that because if you remember your end goal, remember my end goal is I'm trying to get to a 2 cosecant theta, and I'm going to be able to factor out that 2 and get there. So getting kind of excited that I see my goal. So if I look at the numerator, I can take out a 2 secant theta as a GCF, leaving me with a secant theta plus 1. Oh, I'm loving that because what can happen in the denominator? I can cancel out those two expressions. Remember that addition is commutative, so it doesn't make a difference if it's secant theta plus 1 or plus 1 plus secant theta. Those are equivalent statements. And so I am left with the numerator is 2 times 1 over cosine theta. Tangent by the quotient identities is sine over cosine, right? But when you divide, it's same as multiplying by the reciprocal. So that would be cosine theta over sine theta. And friends, your inner math nerd does the happy dance. The cosines cancel. 2 over sine theta does give me 2 cosecant theta. And I have successfully verified this identity. Let's go to example 9. Example 9 and example 10, we're done. All right. On this problem, I'm going to be real upfront with you. I don't know which side is really the most difficult side. I'm letting you know that my personal preference is I think it's easier to turn a sum into a product than it is to go to vice versa, but that's just my personal preference and how I'm going to look at this. Okay, this is a prime example of look at your goal. I'm trying to take tangent and cotangent and put it into secant cosecants. You do have an option that like I could put this both in cotangent, right? I could put this both in terms of tangent. But my goal is secant and cosecant. What do they have in common? Sine and cosine. So I'm going to make the choice and use the quotient identities and rewrite tangent as the sine of x over the cosine of x. Rewrite the cotangent as the cosine of x over the sine x, because that's what they have in common with secant and cosecant. All right, we've been there, done that. Get used to. If you don't like getting common denominators, welcome to Identities. So I'm going to go ahead and let me erase. In order to get a common denominator, I need to rewrite this as sine x over sine x so that I get sine squared x all over my common denominator of sine x cosine x. I'm going to rewrite this, or excuse me, I'm going to multiply this rational expression in order to get my common denominator by cosine x over cosine x, which gives me cosine squared x. Do you see it? Are you doing the happy dance? Look at it. This is the Pythagorean identity, which is 1. And think about, what is 1 over sine x? Well, that's the cosecant of x. What is 1 over cosine x? That's the secant of x. Depending on your teacher, I would accept this as a final answer, but since you do have multiplication as commutative, you of course can write it as secant x. Cosecant x equals secant x cosecant x. And our last example. If you have tuned me out, don't tune me out yet, because there is something in this problem that we have to talk about. It is a strategy that we have not discussed, and that is where sometimes you are going to have to use a conjugate. And I want to show you when this pops up. It's usually pretty obvious when a conjugate is needed. All right. Secant x plus tangent x is equal to cosine x 1 minus sine x. I'm going to let you know that in this problem, you could really start with either side. For teaching purposes, I am going to start on the left. So, on the left, I'm going to turn everything in terms of sines and cosines because I'm looking at my goal. My goal right here, everything is in terms of cosines and sines. So the secant of x would be 1 over the cosine x plus sine x over cosine x. And you're like, well, that's kind of nice. That's dandy. We already have a common denominator, so it's 1 plus sine x over cosine x. And this is where kids go, what the heck do I do? They're not squared, so I can't use Pythagorean identities. I already have things in its most basic form, sine and cosine. So this is what I mean by you have to use a conjugate. How do I know? Isn't it just a hair suspicious that I have a 1 plus sine x in the numerator and a 1 minus sine x is my goal in the denominator? Aren't those conjugate pairs? That is usually screaming multiply by a conjugate. So I'm going to be fair, friends. You at this point, you could, if you wanted to, start with the right side and make it look like the left. It's just going to be my work backwards. And some kids have asked, can I work on both sides? And the answer is yes. You can work on both sides. You can make the left look like the right by working on them, and what I want to be clear, separately. It is valid to work on both sides separately. As a reminder, you cannot use an equation operation. You cannot add sign to both sides or subtract or multiply or divide or square both sides. You haven't verified that the initial statement is true yet, but it is valid to go ahead and work separately on each side and then make each side match if that is a strategy that works for you. All right, so here we go. Let me show you how to use a conjugate. When you use a conjugate, remember that you can only ever multiply a rational expression by the number 1 for it to stay equivalent. So I'm going to go ahead and multiply both sides, both the numerator and the denominator, by 1 minus sine x over 1 minus sine x. In the numerator, first, outer, inner, last, I end up with 1 minus sine squared x all over cosine x, 1 minus sine of x. Now look at your goal, friends. Look at your goal. My goal is to get a 1 minus sine x on bottom. I have that, so I don't want that to cancel. I need to get somehow this cosine to cancel, right? Well, in order to get the cosine to cancel, I need some type of cosine on top, right? Well, we've got a Pythagorean identity. This gives me cosine squared x. And then, do you see it? Come on, move up. This cosine cancels out that. And cosine x over 1 minus sine x equals the cosine of x 1 minus sine x. And friends, if you wanted to start with this side, then all of your work would have been in this direction. So now you're ready to start verifying identities yourself. You do have a book assignment, so you're going to go old school. And you're going to show me work on a piece of paper and upload that by using a PDF where you type your last name, .unit1, lesson4.pdf, and enjoy.